Hello everyone, my name is Louis and I graduated in 2024 with an 8 star of 99.55 and got 50 out of 50 on the physics external, and I'm here to show you how you can achieve those types of scores. Okay, and please watch my first video on the multiple choice papers as it has lots of principles such as the 5 F's, as we'll be going throughout this paper. One short response for 2024 physics. Okay, and I also have links to my OneNote, and thanks for all your support in terms of my physics videos. I'll definitely be working on these as these have got the most views and likes, so I hope this can help and benefit many of you. But if you have any suggestions or specific ones you want me to go through, please let me know in the comments or message me on my Instagram, Louis Galman. Okay, let's go straight into it. So, describe the particle interaction shown. We have a Feynman diagram here, and you should be really familiar with Feynman diagrams. I believe there's a PDF on the QCAA website for physics on all the Feynman diagrams you need to know, and these are the ones that they could only possibly show you. Okay, they probably won't show all of them, but it's good to know what they do and be familiar with them so you can answer these high yield questions, 3 marks, very easy. If you know what you're doing, you know what the symbols are, and you know the particle interaction. So the first mark is by identifying that there's an interaction between, or that involves, an electron and positron. How do I know that? Because an electron is a symbol E negative, and then the positive version of that is a positron, the E positive. Okay, so we know from Feynman diagram principles, this is also on the PDF, that and positive charge particles in a space-time diagram, their arrows go in the opposite direction. So what the positrons are actually doing are they're moving from left to right. Okay, and with the electrons, which are negatively charged, then the arrows just go in the same direction. Okay, and so what happens here is that they interact. Okay, they meet at a specific point, right? So that's your first mark, very simple. And then what happens now is you have to discuss what happens in the second step. Okay, what type of interaction is that? We know that this is right here, that's an annihilation reaction. Okay, or interaction, sorry. So the second mark is really just saying two particles, or the two particles, are annihilated into a what? What's this symbol? That gamma symbol is a photon. Okay, so again, special relativity, this really just rote learning. You need to know what these symbols are. And then the photon will therefore pair produce, which is a special term that is required in you to know in the standard model. Sorry, I think I might have said special relativity. This is not special relativity, my bad. But the standard model, photon pair produce another electron and positron. Boom, that's it. Okay, 3 marks there. All right, so what happens after is that we have this photon coming that was produced from the annihilation of an electron and positron, and that produces in the opposite direction a positron and an electron. Okay, so the particles just go in the opposite direction. So the electron was going in this direction, now it's going in this direction. Okay, all right, and so that's what we call a pair produce, because we have two particles, the electron and the positron, that are produced, right, by the photon. as time goes on from left to right. So question 22. Special relativity accounts for the observation that more muons from cosmic rays are detected near Earth's surface than expected. Explain this phenomenon by outlining why Newtonian physics cannot explain this scenario, while special relativity can. Refer to the frames of reference for both the traveling muons and the observer near the Earth's surface. Okay, so I've just highlighted the key cognitive verbs as well as the key information that the question is really asking us to do. Okay, so let's break this down. So let's look at Newton's view. So what we'd expect as the observer on Earth. Okay, so we can say that muons are subatomic particles created when cosmic rays hit Earth's atmosphere. Okay, so that requires us to know a little bit more about the muons theory about them, and that is one of your key dot points in what you need to know for the externals in physics, right? So you need to know a couple of theories such as the muon theory in terms of special relativity and why Newtonian physics cannot explain it, right? So that's one of the like a context statement you can make, but the real first mark you get is saying that muons have a very short half-life. Okay, and if you want to remember, it's about 2.2 microseconds. Okay, so that symbol there, mu, just means micro. Okay, so you get a tick by saying that muons have a very short half-life. Okay, apologies. The next mark you get is saying how Newton or Newtonian physics won't be able to predict correctly and accurately the scenario as above, right? The observation that more muons from cosmic rays are detected near Earth's surface than expected. Okay, so according to Newtonian physics, even if the muons are traveling at even close to the speed of light, they, as in the muons, should not survive the full trip to Earth's surface. Okay, because these muons are decaying with a very short half-life very rapidly, and they have to travel from cosmic rays in Earth's atmosphere, or like beyond Earth's atmosphere, and they have to travel this large distance to get to the Earth's surface. According to Newton's physics, they should not make it in time. All right. Okay. And therefore, we'd expect them to decay mid-air and barely reach the ground. Okay, and so that's where our second mark comes from, is really just saying that the muons are unlikely to reach Earth's surface using Newtonian physics. Okay, what do I mean by Newtonian physics? Simple. Speed equals distance over time. Okay. And those sort of observations, like half-life and things. Okay, if you have such a large distance, okay, and so little time, it really can't if you were to rearrange the speed distance time formula where we have such little time for it to survive, and well, we do have muons reaching approximately the speed of light, but not at the speed of light. Okay, and we have so little time, that doesn't really account for such a large distance. Okay, the distance should maybe be a bit middle between those two, but it isn't. We have such a large distance, small amount of time, and close to but not at the speed of light. So if you want to do your calculations, feel free to do that, where you just take the mu1 half-life and the distance of Earth, and you compare that with this formula for the left-hand side. You calculate that, you'll find that the distance is significantly smaller than the distance between cosmic rays and Earth's surface. Okay, so that explains why Newtonian physics cannot explain the scenario or observation. And yeah, just saying that Newton predicts that the muons won't make it to Earth's surface. Okay, moving on though is where we have to talk about basically Einstein's turn, okay, where special relativity can actually explain this scenario and brings a solution to the observation, a scientific solution. All right, so you'll get a mark for identifying that muons travel at relativistic speeds. Okay, so it's a simple mark to get, but you really need to remember that special relativity requires the objects, such as the muons, to travel at relativistic speeds. So what does that mean? It means that they travel very close to the speed of light. Okay, and so according to Einstein, or special relativity, whatever you want to say, at these speeds, the relativistic speeds, we need to consider time dilation and length contraction. Okay. So that's where our third mark. So we have 5 marks in this question, right? That's where our third mark comes from. Just saying that muons travel at relativistic speeds. And that leads on to why we can talk about special relativity and how we can apply those principles of special relativity, because muons are traveling at really, really fast speeds, close to the speed of light. Okay. Now on to the fourth mark, is essentially just answering this second part of the question. Okay, you need to have the frame of reference of both the traveling muons, so that's 1 mark, and the second mark is the frame of reference of the observer near the Earth's surface. Okay, so let's do the Earth observer's frame of reference. Okay, I don't think it really matters what order you do it in. As long as you have the information there, you still get the marks. Okay, so we can say that from our frame standing on Earth, the muons, internal clock ticks slower because of time dilation. All right, and this makes it look like the muons live longer than 2.2 microseconds. Okay, therefore they survive long enough to reach the surface. Okay, so that's where our fourth mark comes from. Essentially saying that from the observer's frame, time is dilated. Muons last longer. Okay? Because if we are a stationary observer on Earth, this is us, and we're watching these muons come at us really, really quickly, we will observe a time dilation or increase in time for their survival and their travel towards Earth's surface. Okay? Because the key principle there in special relativity is that time ticks slower for things that are going at relativistic speeds from the frame of reference of a stationary observer. Okay? Now, moving on to the last mark, which is the muons frame of reference. Okay, so what happens here? Their they won't experience time dilation for themselves. They still have the same half-life, the 2.2 microseconds. But what they're observing in the muons frame of reference, what are they observing? They're observing the distance between them from the cosmic rays to Earth. Okay, and so this now links to length contraction. Okay, and it makes sense, right? If their half-life and survival time is increasing for Earth, then that means on the muons frame of reference there is a shortening of length, and that both overall helps to allow the muons to reach Earth's surface and not decay, right? Because if they're traveling at relativistic speeds, they need to reach a distance. But if they can shorten that distance by traveling to relativistic speeds and experiencing length contraction, then they're going to survive, right? So remember our formula with speed in Newtonian physics. Okay, if there was a way to actually change the distance, the real distance from Earth to from Earth's surface to the cosmic rays, then we might actually get the muons to make it. Okay, so they're experiencing length contraction now. So from the muons point of view, it is not living longer. Instead, it sees the atmosphere as being squished due to length contraction. Okay, so imagine that this is the atmosphere of the Earth and it's being squished down. So if I were to copy this diagram we've made, I can hopefully try and show it to you better. Alright, so say that I'm decreasing this size now. Okay, so this is what it is like now, right? The distance has decreased. Atmospheric distance, same here, okay? Atmospheric distance, okay? And because they're traveling so fast, close to the speed of light at relativistic speeds, that distance they're traveling is actually going to decrease from their point of view, their frame of reference. Okay? And so we can say that the distance to Earth is much shorter. Okay? So even in its short life, it can still make it to the ground. Alright, and that's our fifth and final tick and mark. Alright, so that's a full mark question right there. Alright, response. So that last mark is really about saying that from the muon's frame of reference, the atmosphere is shorter thanks to length contraction. Alright, so in summary, I know this is a big question, and during my external exam when I did this question, I actually went multiple pages. I went to the back of the book and I wrote my page numbers and everything, question number, and I just went all through. I think I used like 2 pages. I even went above and beyond to give calculations and the exact numbers and comparing them, and using this formula here as well as the formulas in the formula book for special relativity to explain why it works, and so my recommendation for these questions, if you have time, you speed through the multiple choice. During your perusal time, you just look and I guess sort of mark in your head, or using your fingers, just your answers to the easy multiple choice questions, so you can really speed those through and have plenty of time to work through these. Okay, I remember I think it took me like less than 10 minutes to do multiple choice because I had already planned ahead during my 10-minute perusal time doing all the multiple choice, so I could go straight to here and give as much detail as possible. Okay, you will not lose marks by having too much detail, but you will lose marks if you forget stuff like, for example, the marking scheme saying that you need to say muons have a very short half-life. That can easily be missed. You might just immediately go by talking about Newtonian physics or doing what the question asks, but you need to explain why, and that involves a lot of theory. Okay, and in order to memorize that theory, that's a lot sometimes. All right, and so if you write as much as you can close the gap or close the probability of you possibly forgetting something. All right, cool. So yeah, in summary, Newtonian physics doesn't cut it. Special relativity, though, it explains it perfectly, and that's why we detect way more muons on Earth than Newton predicted. Okay, so moving on to question 23. An experiment was conducted to study an object undergoing circular motion, with the radius of motion acting as the independent variable and the speed kept constant. Okay, so we know independent variables on the x-axis and speeds constant here. So data comparing the period and radius of motion is shown. Okay, now literally when I saw this question on the exam, I was like, this is like year 7 maths, year 8 maths, honestly, right? So identify the period expected for a 25 centimeter radius of motion. All right, we convert that to meters or SI units, which as well as the graph is in, which is good. So 25 centimeters, we know that there's 100 centimeters in a meter. All right, so that's how we just convert. We divide by 100, and that gives us 0.25 meters. Okay, but that's not our answer. That is the radius, but we need to find the period expected. All right, so periods in seconds, so the y-axis. So literally all you do is you find the middle point of 0.2 and 0.3, because that's give you the 0.25 value. Okay, and then you use a ruler. I don't have a ruler on my OneNote iPad, but you really got to use a ruler for this. Draw a straight line. Okay, you have to draw a straight line. You can't just be lazy and just put the answer down, because sometimes you'll get marks for drawing the line. Okay, because you need to identify and show the marker you're working out always. All right, so I think that'd be close to and for some reason this in my year, last year I did the external exams, they didn't put the number of significant figures to put down, so I just based it on the graph. The graph has 2 significant figures or 2 decimal places, so I just did that. Okay, so honestly, if it's 2 decimal places and I have my 0.21, 0.22, 0.23, 0.24 on my graph on the line, I'll just say 0.21. And then I don't need my units here because the box already has the units, but make sure you write that on the box. Okay, so yeah, just really make sure, don't risk losing marks. You have to show all you're working out. Okay, even write down the 0.25 here. Okay, and everything, and circle where you found the 0.21 on the graph. Okay, because sometimes, especially with graphs, some weird things can happen, right? Where maybe you miscalculated a reading, but you might still be able to get part marks, like throughout this question, for example, if the marker knows what mistake you made and can give you follow-through errors. All right, so say that, for example, whatever reason you chose this value as 0.22 seconds. Okay, you might lose that mark, but because the marker knows on the graph how you got that mistake. Okay, so maybe you write 0.22 here. All right, for example, the marker can be more lenient towards you and give you full marks for option B if you need to use stuff from part A. Okay, for example. All right, so always remember to bring your ruler to the physics, or get a ruler before your exam and utilize it. Okay, you cannot be sacrificing easy marks like this where it's just 1 mark. Okay, they were very generous here. Okay, so now the actual physics. So we need to determine the constant speed of the object. Okay, show you working. So what we need to do here, in any graph we do, most of the time at least, we calculate the gradient. Okay, so we need to write gradient. Okay, be very clear on what you're calculating. Don't say m, lowercase m. Okay, that's used a lot in maths, but in physics you need to be very clear because it's part of the marking scheme. y2 minus y1 over, x2 minus x1. Okay, and then I would choose my 2 points. Okay, I want to choose 2 points that are on the line. Okay, it has to be on the line. Don't use points that are dots. Okay, that's a common mistake. I want to use 2 points that are as furthest away as possible, but still gives me a good coordinates and good numbers to work with. Okay, so I'll probably use this point because that's literally on the dot. Okay, so 0.10 comma 0.10. Okay, and so that I would label that as soon as possible so I don't get my numbers mixed up as my x1, y1, because this is my first coordinate. Okay, and then I'll see, and I'll think about and then I'll see, and you can see that they've been very generous with how they've done this graph. Okay, it is both endpoints are literally on the line. Okay, so there's no excuse for you to use these 2 points that are furthest away from each other, and gives you really good values to work with. Okay, so that's going to be my x2 and y2. All right, 0.40, 0.4, they're all the same, but I guess just to be safe we would write the actual exact number from the graph, because it shows us how we're using the graph, if that makes sense, you know. So from here I would just plug those points into the formula. Okay, because I've labeled those points as my x1, x2, etc. Sorry. Okay, and then I'll get 0.30, 0.40. I'm just doing this in my head, and that will give me 3/4 or just 0.75. Okay, but you know, don't sacrifice. You have a calculator. Okay, you can use your even graphics calculator for physics, thankfully. So really utilize your calculator. Okay, you don't need to be stressing on doing the maths and showing you working out for specifically these ones. You won't get the marks for that. Okay, you'll get the mark for calculating the correct gradient. Okay, and also perhaps having the units as well. So saying the gradient is, you know, in terms of seconds per meter. Okay, and saying how you're rounding it to. So 2 significant figures. Or you can just do SF, I think. Can work as well. But really you just gotta, my bad. You just have to put this into the calculator. Okay? You'll still get full marks. And it saves you time as well. And make sure that you're as accurate as possible. Okay? And then now what we do is we use the formula. So I don't have it me right now on this page, but I will add it right now. Okay, so I've now added the formula book to the side. And so if we're using you know, the 5 F's, and we have our facts, so we know the gradient, we know our, well, we had found our x1, y1 and stuff, but really what matters here in terms of the maths is the formula, the variables. Okay, so our facts are that we know this is circular motion. Okay, that's as if I've highlighted, and the radius of motion, so that's going to be my lowercase r, and the speed, but in circular motion we call that as lowercase v. Okay, because it'll always be constant. And so we can now use a formula that gives us those variables as well. Oh, and also period is also on the y-axis, so I'll just say that, oh yeah, here, this next sentence, data comparing the period, so that's my capital T. Okay, and so I need to find a formula that uses lowercase v, lowercase r, and uppercase T. So I'll just go to my gravity in motion. I know where I can find it. It's this formula right here, v equals 2 pi r over t, big T. Okay, so what I do now is I say since v equals 2 pi r over capital T, then what I can do is I can rearrange the formula to get my gradient. So remember, from my gradient is period, so y over x, right? Changing y over changing x. So using my variables, I know that the gradient is the period, or capital T, over my x value, which is the radius. Okay, so I need to rearrange the formula somehow to get to a point where I have T over R. Okay, so I need to transpose my formula. So what I could do is I could put the T on the top. So in doing that, I just swap my V and T, because it's a little trick you can do in maths. If you're trying to transpose, you'll still be given an equal equation, right? And I can do a quick proof of that if you wish. So if I have V equals 2 pi r over capital T, if I put a 1 here and I just cross multiply, and that'll still be equating 2 pi r times 1, which is just 2 pi r over Vt. Okay, and then I just divide by V on both sides. I have 2 pi r over V equals capital T, because these V's cancel. So you can see here that all I've done is just swap these two around from the original formula, which was V equals 2 pi r over capital T. All right, so that's an easy trick you can do to save time as well. Okay, so now that I have T not on the bottom of a fraction, but it can be on the top of a fraction, then I know that I just need r on the bottom, so I can just divide by r on both sides. Okay, so I'll just do T over r equals 2 pi on V, because I'm canceling out the r's on the right hand side. And so what happens now is that I have two equivalent expressions, like simultaneous equations. My T over r is my gradient, but now I have a different formula for my gradient. It's going to be 2 pi on V. Okay, and so from that, I can just rearrange my formula now to find V, which is this constant speed of the object, right? So that implies that V, so again, doing that trick where I'm, swapping these two variables around on the bottom of the denominator, V equals 2 pi over gradient. Okay, and therefore 2 pi over, and what was my gradient? It was 0.75. My 2 pi over the 0.75 will give me an answer of 8.38 meters per second. Okay, so I need to make sure I put that in the box. Okay, you don't want to lose silly marks because it's not in the box. And so those are my full marks there for 3 marks. So where do my 3 marks come from? Calculate the gradient, recognize the relationship between gradient and average speed. So noticing that we have a gradient equals 2 pi over V. Okay, that's where the mark comes from. Not writing the formula from the formula book, it's rearranging and getting the final transposition where we have gradient equals something, okay, in terms of the variables of physics that we're using. Okay, right, so you need to make sure that you have the formula for the gradient that you found that is correct. Okay, all right, and then obviously the last step would be calculating the constant speed of the object, as what the question asks. Okay, But remember, show you're working, all right? In order to get to 8.38, you need to have done all these steps, so make sure you write them down, okay? Question 24 has 7 marks. The atomic energy level diagram for an unknown multi-electron ion is shown, okay? And we want to calculate the wavelength of light emitted as electrons move from n equals 4 to n equals 2. Show you working, and this is 4 marks, so this is a really high yield question. Now really, it's a pretty easy question if you know what you're doing, okay, to get full marks. The first mark is literally doing subtraction, okay? So you need to calculate the change in energy between n equals 2 and n equals 4 energy levels, and that will be your first mark, okay? So you need to show that energy change for the n equals 4 to n equals 2 transition is 13.6, right? Minus the 3.4, okay? And the reason we're doing we're removing the negatives is because if you think about just the distance between them, they're going to be the same, okay? Like I'm essentially just doing, if you wanted, I can do n equals 4 minus n equals 2, which will give me negative 3.4 minus 13.6, okay, which is just the same as negative 3.4 plus 13.6, okay, which is the same as what I wrote before, okay? And so that gives me 10.2 EV, okay? So the key thing about this question to make sure you get the full marks is making sure you have the units, okay? Because you will get only the first mark if you have EV in there. And just to be 100% accurate, making sure that you're only writing within the line, the box, okay? As it says, do not write outside this box. So 10.2 EV, or electron volts, okay? The next part of the question requires us to convert the electron volts into joules, and the reason for that is because we're using a formula that only requires joules, okay? So this formula, I believe would be quantum theory, yep. E equals hf, that's going to be one of the formulas we're using, right? And E is energy, all right? And energy is always in joules because that's the SI unit for joules, all right? So, and it will become more clear if we do the facts as well, which I will get to, right? So doing facts, insert the 5 F's, so E equals 10.2 EV, right? H, which is in terms of, wavelength and all these quantum theory things, H is a value we know, and it's in our formula sheet. It's 6.626 times 10 to the negative 34 joules times second, okay? 626 times 10 to the negative 34 joules second, okay? So you can easily recognize here that we need to be in joules. We can't be working in EV, okay? Because in our formula, E equals HF, where frequency, the units for that is actually in hertz, which is per second. We know that we have if we put our units in, so H is joules times second, and we times it by a unit for per second, we're only left with joules, okay, for the energy, right? As the unit for energy is joules. And so we need to make sure our energy is not in electron volts but in joules. Okay, and the way to do that, and this is the second mark, by the way, right? If you don't believe me, look at the marking guide. The mark you get is by doing this essentially, okay? That 1 EV equals 1.60 times 10 to the negative 19 joules, okay? So we can write that down if you want to. So 1 EV equals 1.60 times 10 to the negative 19 joules. Okay, if so, that means if we want to convert from EV to joules, we have to multiply by that number, 1.60 times 10 to the negative 19 joules, okay? Because we're going from left to right in the equation, and to get the value from 1 to 1.60 times 10 to the negative 19, we're multiplying by that number, okay? And so it's essentially what I'm doing here. So 1.6 times 10 to the negative 19 joules per 1 EV. Those EVs will cancel out, and we'll get a value for that, okay? I'm not going to put that in my calculator though. I'm just going to keep that value, okay? Because I don't want to be rounding or doing anything like that. I want exact values throughout my entire like solution until I get to the final answer, which is for the wavelength, which I might round or make into scientific notation depending on my answer, right? So that's going to be my energy. So I might rewrite that so it's a bit clearer. It's going to be 10.2, which was my EV, but I'm converting it to joules, and because 1 EV is 1.6 times 10 to the negative 19 joules, then I'm just multiplying by that factor, okay? All right. Now, we don't have frequency, so what do we do, right? So I guess our second mark, is where we get the energy in joules, okay? So that is our energy in joules, second mark. The third mark is by the formula section, okay? So we've done the first 3 5Fs, right, which is facts. We have our at least some of our facts. The figure, which is already given, we don't have to draw it again, and the formula is now our third F we need to do, right? And so if you've done these questions before, you'll be very familiar that we need to use a formula from year 11, okay, assumed knowledge. It is in waves when we did unit 2. The formula is V equals F lambda, okay? Or speed velocity equals F lambda. Okay, so V equals F lambda. Now, in terms of quantum theory, what is speed? Speed is always going to be c, which is the speed of light, right? And we know c equals 3 times 10 to the 8 meters per second, okay? And so that's another fact we can add, as well as our formulas. Now, we don't know what frequency is, but we can rearrange this formula right here to have frequency on one side of the equation, and then just use that to figure out what we need, right? And another fact we sort of know is we're trying to find wavelength, and the wavelength symbol is lambda, like that. Okay, it's like a sort of backwards H, if you want to call it like that. Okay, and it'll be question mark meters, okay, as our SI unit. And that's what we're trying to find, wavelength, right? So this works, okay? So if you didn't know that, maybe you could go and have a look at which formulas use lambda, okay? But I guess it would have been difficult because you might have been using lambda, these ones, but they don't work, okay? And in fact, I'll tell you which equations we never had to use in the externals, or based on past externals I never had to see or use. It was this one, this one, this one, and this one. Okay, I believe they were never used in past externals or let alone last year's. So just something to keep in mind. I think they're just extra formulas, but they're not actually related to the key dot points, like the I think the ray dig. But I think they might be useful in determining relationships. I'm not too sure, but yeah, if you end up using one of these formulas that I've circled in red for quantum theory, then I'd be just really careful and make sure you're really having the right variables here. Okay. I don't know why they put it there, and I don't know why we don't use them, but that's my best guess. Right? So we'll have to resort to using year 11 formulas, okay? So the year 11 formulas we really need to use, I think are this one, and that's really it. Okay, you won't be working with sine, okay? In terms of the waves, you won't be working with the different types of sort of sound waves, I guess. And you won't be needing intensity of light and stuff. So those are the two from there that you need to know, I guess. And I guess linear motion, you sort of have to know how to apply them as well. Okay, sorry for my rant, just wanted to let you guys know. But transposing, right? So we want f on one side of the equation, so let's get rid of lambda from the right hand side by dividing, okay? Because we're multiplying here, so we have to divide to get to do the opposite. So we know c over lambda is now equal to f. Okay, we have this formula now for f, or frequency, lowercase f, and I can plug that into this formula here, right? So therefore, E equals hc over lambda. Okay, so wavelength is h, which is 6.626 times 10 to negative 34. This is our substitute section, times the speed of light, which is c, or 3 times 10 to the power of 8. And just letting you know, these values, they're given to you in the formula book, so use them. Okay, we have the speed of light in a vacuum from year 11, and we also have the Planck's constant there. Okay, and then that's divided over the energy. Sorry, I was meant to transpose this. So wavelength equals hc over energy, right? So we just swap those around once again. Okay, so you know now how really beneficial and helpful that trick is, where you can just swap those two variables and numbers around from the bottom of the fraction and to the other side of the equation. So the energy we found was this value right here, 10.2 times 1.6 times 10 to the negative 19. Okay, and I'm going to plug this in my calculator now. Making sure you really get the correct numbers, okay? Making sure you have your negatives correct as well. Being very careful. Okay, and you should get a value of approximately 1.22 times 10 to the negative 7 meters for the wavelength. Okay. And so you would put that as your answer because it's a really small number, and so we use scientific notation to represent that in meters. Okay. Making sure our units are correct. Our finalized stage, the last of the 5 F's, making sure we have all the working out, all the marks. So that was really 4 marks. All right, so the third mark we got is from showing that E is equal to hc over lambda. Okay, so you're just basically transposing, combining those two formulas, and then calculating the correct wavelength is obviously the fourth and final mark. Okay, putting it in the box in the right units and right format. Okay. let's see this one. A photon with 40.8 eV of energy is incident on the unknown ion and collides with an electron in the first energy level. Explain what would happen within the ion in terms of the photon and electron. Okay, so let's see here. All right, so I can say that the photon will be absorbed. All right, and the reason for that is because we know at energy level 1, if we add 40.8 EVs to our n equals 1 energy, because we're told that a photon with 40.8 eV of energy is incident on the unknown ion and collides with an electron in the first energy level. If we do a quick calculation, negative 54.4 plus 40.8 eV, we get a value of negative 13.6 eV, which corresponds with the n equals 2 electron energy level. Okay, and so that's our first mark, because we know it will be absorbed, and the reason for that is because since the photon energy of 40.8 eV corresponds to the difference in energies between the first and second energy levels, an electron in the first energy level, which is our n equals 1, will absorb the photon and jump to n equals 2, the second energy level, in its excited state. Okay, so really that second mark out of the three marks you get here is explaining that 40.8 eV is the difference between the first and second energy levels. So basically what we did here with some simple addition. Okay, and then really that third mark is just saying that an electron will jump from n equals 1 to n equals 2. Okay, so therefore it will be the electron in the first energy level, right? So this is an electron. So say this is my atom, right? This is the electron. It will absorb that photon, right? Take that energy and use it to jump to a higher energy level, n equals 2. Okay, so it will just jump and move there. Okay, so that's essentially what happens, right? So if an electron gains more energy, it's going to go more outer of the cell and go to higher energy levels. Okay, from n equals 1 to n equals 2, for example. Okay, so that's essentially what's happening. All right. Question 24. A transformer with a turns ratio of 48:1 is set up to reduce a 240 volt input. Explain how a transformer works in terms of Faraday's law and electromagnetic induction. Okay, so it seems to be quite clear on where the marks come from here. So the first mark is really just describing Faraday's law. Okay, so we can say according to Faraday's law, when the magnetic flux linking to a circuit changes, an EMF is induced in the circuit proportional to the rate of change of the flux linkage. Now, I'm pretty sure this is in the glossary for definitions you need to know in terms of the dot points about Faraday's law. But if you ever got stuck and you know your formulas and you're more of a math person, then you can just simply know that these two formulas here are Faraday's law. Okay, and what I've written out is literally just describes that formula. So according to Faraday's law, these formulas, you can even write them down if you want to. Okay, you can write both, but I'm just going to write this one because it's more, the second one, because it's more about a rate of change of something. Negative n delta delta t. Okay, so just think about it. If we just, I guess, think of our negative n as our outside sort of variable, then magnetic flux linking to a circuit changes, right? So because we have a change in these triangle symbols, they're called delta, and they just mean change. Okay, so when the magnetic flux, which is our this symbol right here on top, linking to a circuit changes, an EMF, which is what our formula has, is induced in the current proportional to what? Well, if we took this negative n as our outside variable and we just take this as k, imagine what will happen if we increase k, our delta magnetic flux over delta t, right? If we increase our k, then what will happen to EMF if we just think of the proportionality? We know that's going to increase, right? So if one increases, then the other will increase as a whole. Okay, so that's why it's proportional to the rate of change, because the rate of change is a fraction. That's what this is right here. Okay, the delta magnetic flux over delta time. Okay, that's essentially like a gradient, like a y over x, change in y, change in x, for example. Okay, so that's involving a rate of change of the flux linkage. Okay, and so really what I did for that first mark in terms of describing Faraday's law is just looking at the formula and writing about what it is about. Okay, and then now I have to link it to how transformers work as well as electromagnetic induction. Okay, so I can say, therefore, in the transformer, the changing voltage in the primary coil will affect the rate of change of the magnetic flux in the second coil. Okay, and what happens there is, because we have a voltage, then a current will also be induced. But only in the secondary current circuit. Okay, so if I were to draw a diagram, I could show how we have the primary coil, alright, and it's connected to a secondary coil. Okay, and then if magnetic flux changes, so say it will increase because there's more surface area now, which is, part of that first formula is that magnetic flux is proportional to the area. Then what will happen is we have and over time, then what will happen then is that an EMF is induced. Okay, and when EMF is induced, which is proportional to that rate of change over time in the magnetic flux, then the changing voltage in the primary coil, right, will affect the rate of change of magnetic flux. So primary affects secondary. Okay, and then we can also draw some arrows here around the secondary coil. Because of that changing magnetic flux and the voltage and everything, we have to have a current. This is I, capital I, which is representative of current. Okay, so where the marks come from, you need to explain that a changing voltage in the primary coil affects the rate of change of magnetic flux in the secondary coil. Okay, so really that second mark is here, that second sentence. Okay, so even simpler, you can think of it or remember it as the changing voltage of the primary will affect the rate of change of the magnetic flux in the secondary coil. Okay, so that's where your second mark comes from, and mentioning now how basically the AC voltage is induced in the secondary coil by electromagnetic induction. Okay, so you can also link this last sentence a bit more to electromagnetic induction. Okay, because if we have changes in the magnetic flux, then electricity can also flow through there, and that links to a current being induced. Okay, now determine the output voltage. All right, so this one requires us to use a bit of maths now. So let's do the 5Fs out, shall we? So let's say that we have the turns ratio 48:1. So what is that in our formula? So if you need to have a quick sneak peek in the formula ahead of time, please do so. But this is the transformers formula if we have a ratio, because our n variables are the ratios. Okay, so we have n1, which is 48. Sorry, n primary, because we're going from primary to secondary coils, and ns, which is our secondary number of turns. All right, and then what else do we know? What are facts do we know? We have the voltage of the primary, because it's saying we have set up to reduce this input, so that means it has to be the original, or like primary first voltage that we're trying to deal with. Okay, and again, output voltage, that's just the secondary voltage. Okay, because remember from part A, we move from the primary coil to the secondary coil. All right, so we know that the secondary voltage, or Vs, is question mark number of volts. Okay, and we have that box there to confirm. All right, so now we can draw a figure, okay, if we wanted to, but I've already done that here on part A. Yeah, I guess at this point what we can do now is just go straight to the formula, to be honest. It's only 1 mark, so you know that this isn't one that you just require a lot of working out. You really just get a mark for the answer. Okay, equals n. So that's taken directly, I believe, from the formula. Yeah. Okay, and we just plug in our values, or we can transpose. So if I were to transpose this and get the Vs on one side of the equation, what I would do is, well, another trick in math is I can flip these fractions around, both of them, because whatever you do to one side you do to the other, and then they're going to be equal now. And once I've done that, I just have my variable at the top, so I get rid of the bottom by timesing by Vp. Okay, so my secondary voltage is now equal to the number of turns in the secondary coil times the voltage of the primary coil over the number of turns in the primary coil. Okay, I just substitute my values now because I know them. It's going to be 1 times 240 over 48. Okay, and that gives me 5 volts. Okay, so that's my answer there, 5. Okay, and that's my 1 mark there. Okay, so that's a total of 4 marks, full marks in that question. All right, 2 more questions to go. 3 marks, just this one question. The centers of 2 small equally positively charged metallic spheres are separated by a distance of 0.30 meters and experience a force of 0.025 newtons between them. Calculate the charge on each of the metallic spheres. Show you working out. Okay, so let's do our facts. 5Fs. R is equal to, because we know in terms of electricity and stuff, in the formula we have R as distance usually, right? So R is equal to 0.30 meters. Is that in SI units? Yes, it is. And the force, or capital F, what's going to be capital F, is 0.025 newtons. Is that in SI units? Yes, it's in newtons. Okay, great. All right, what else do we know? We know that two small equally positively charged metallic spheres. Okay, so that means that Q is equal to big Q. Okay, so if we think of these two charges, they're different but essentially the same. Okay, so what we have in this question, if we draw a diagram, we have two of the exact same equally positively charged metallic spheres. Okay, their distance between them is 0.30 meters from between their centers, and we know that Q equals Q because the charge is equal to the charge here. Okay, they're also equal. Right, and we know they are positive as well. Okay, they're both positive. All right, so they're gonna actually be repelling on each other. All right. Now, what we have to do now is figure out a formula to use. So we're just looking at electromagnetism. This is where electric stuff is. We have force here. Okay, we have Q, Q, R. Okay, so I reckon this is pretty good. Okay, we wouldn't use other formulas like the second one because that has capital E, and we don't. We're not dealing with capital E at the moment. Okay, so let's write that formula down exactly how it is. Okay, so that's our first mark, right? Notice how when we use the 5Fs, we can never miss marks. So the formula. Now what's next after formula and the 5Fs? It's to find. Okay. So we know Coulomb's constant. Okay. Here in the formula book, under electromagnetism, 9 times 10 to the 9. Times 10 to the 9 times QQ. We'll try to figure that out. And then our R is 0.30 and square that. Make sure you square. Don't forget the square. It's a common mistake to forget it. And then we have, so that can be under 1 fraction because we're just doing multiplication and division here. And our force is 0.025 newtons. Okay. Now what could we do here? We could say that because Q equals Q, these two different charges that we have going against each other, we know that we can just substitute one of these into there, and therefore we have, instead of two different charges, we can just let it equal to one charge, and so we have Q times Q, which is the same thing, and so we have Q squared. Okay, and the reason we can do that is because once we find one of the Q's, we know that it's going to be exactly the same as the other Q. Okay, that's why we have to calculate the charge on each of the metallic spheres, and there's only one answer box. Okay, they're not going to be different, they're going to be the same, and so we can combine them and pretend they're both the same like Q value, right? Because they are. So what we can do here is we can just get Q on its own. So this involves a bit of transposing. Okay, remember to be very careful with this. You have Q squared left, so you have to square root this entire thing. Okay, to get Q on its own. And so I'll put that in my calculator now. See what I get. right? And I get a value of Q equals 5 times 10 to the negative 7 coulombs, okay, or 5.0. Right, so that is my answer there, right? And again, I know in previous years, previous to 2024, they used to give us what to round it to, but I don't think they're doing it here because I'm not too sure. Maybe they're don't want people to lose silly marks on rounding errors or something. But as long as you show your full working out, the second mark, sorry, so that was the third mark. The second mark comes from recognizing the charges have the same value in the equation. Okay, so you can get it from there, this formula right here, or you can get it by doing the Q squared. Okay, either one. But I mean, I'm looking at the marking guide now, and it says recognizes the charges have the same value in the equation, 1 mark. So I would, if I was a strict marker, I would only mark you if you wrote this one in the circle. Okay, because from the formula, that's really just implied. Like you could have just made a mistake and thought that these were 2, but you don't actually know that, you know, like I could argue that way. So make sure you give your facts, very important. Say what you know, okay? It's an easy way to get full marks. It's literally just writing down what the question is saying, but in mathematical terms and in physics terms, okay? So 2 small equally positively charged metallic spheres, I'm just going to say Q equals BQ, okay? Last question. This is just one question, but it's 4 marks, so it's really high duty here because this is gravity in motion. On another planet, that's really important, okay? Because if it's another planet, that means G might not be 9.8 meters per second squared, or negative 9.8, okay? An object was projected upwards from an initial height and took 0.71 seconds to land. Okay, we have our diagram. So that's the figure stage done. But we can also draw other figures as well if you wanted to, or like add to the diagram, you know? So the relationship between vertical displacement, meters, and time is SY equals negative 5.18 t squared plus 3.5 t. Determine the horizontal displacement of the object when it lands. Okay, so this is actually an interesting question, a bit of a complex unfamiliar, if you know what I mean. This basically requires you to use assume knowledge from year 11 and use those formulas and know how to apply them. Okay, so when you see this right here, that should be essentially like a ring in the bell for what SY is, right? So we know that from gravity in motion, we know that SY is equal to this, all right? But we also know that that formula is essentially just a representation of this part right here. Okay, so we can use either one, but I'm going to use this one right here, and the reason for that is because I'm given G in my gravity in motion unit 3 year 12 formula, and I know what G is. Okay, I know that G, or the mean acceleration due to gravity on Earth, the magnitude of that is 9.8, and I don't want to confuse myself with G and the actual gravitational force of that's present on this other planet. Okay, so that's why I'm going to use this standard formula, okay, because I know that I can figure out A from that, right? So I know that S is equal to U t plus a half at squared. All right. Now a lot of people might think, how do you go straight there? It doesn't have, horizontal displacement. It doesn't have sx, But sometimes, especially with these 4-mark questions, you need to do a couple of prior steps using different formulas that you can work with in order to get that answer for the final answer of horizontal displacement. Okay. So if you're ever stuck with these sort of questions, just write something that's related. Okay. In year 12, we've been doing sy, t squared, and t. So that should ring alarm bells, even if you use that sy formula, but make sure you don't get mixed up with, making g equals negative 9.8, then you should be okay with this question, okay? It's exactly the same. What I'm going to do now is I'm going to be rewriting this formula, but making sure that it's essentially equivalent with what's happening, right? So I'll show you what that means. So I'll just let this be displacement, okay? I'm not talking about y or anything at the moment. I just want to know that my t variable comes first, because this is like equivalent, so that's what I'm doing. I'm putting them beneath each other so it can clearly be seen a relationship. Minus, remember that minus there, 5.18 t squared. Okay. Cool. Now from that, I can know, so say I used actually the year 12 formula, right? Like whatever. It's still the same thing. I know that my vertical displacement, right? It's when I project an object, I always have x and y components, okay, and to form a right angle triangle. So this is my maybe uy, okay. So this is my u, which is the velocity of the initial velocity of the object as it's projected from this I guess this initial height, okay. And once I know that, I know that I have a ux and a uy to break into right angle triangles, right? So what happens now is that I can see a relationship between these two formulas. I know that if I have t here and a t here, and I have my uy and a 3.5, then I can imply that uy is actually equal to 3.5 meters per second, okay, because they're equivalent. All right. And so what happens now, because I'm trying to find horizontal displacement, I can now work with my formulas here, where I have, if I draw another figure, right, and I use a bit of trigonometry, so I know that's 3.5 meters per second now. I don't know what u is, but I can find out x. Okay. And I know the angle actually. So this honestly just takes a bit of trigonometry, okay? It's not that difficult if you know your trig to see that you have an angle, you have an opposite side, and you have an adjacent side. So what are we using? So ka toa, I have an opposite adjacent side and I have an angle, so I'm going to use tan, okay? So if you can't figure that out quickly, it's okay. just draw your figure and draw the SOHCAHTOA and use whatever formula you need to use. So let's say tan theta equals opposite over adjacent. Okay, very simple. Now I'm just going to put in my values now. So tan of 30 degrees is equal to opposite, which is my uy, over ux, which is my adjacent to the angle. Okay, adjacent to the angle and opposite to the angle. And then from there, I can rearrange to find out what I need, which is ux. Again, using that swap around trick, I know that ux is equal to, well, let's just say uy 3.5 meters, because we know that from our previous step, 3.5 meters per second over the tan 30 degrees. Now again, making sure I'm in degrees mode in my calculator, 3.5 over tan 30. My ux is therefore 6.06 meters per second, and it's to the right, because remember, velocity always has magnitude and direction. Okay, so let's look at what marks we get. We get a mark for understanding that this involves trigonometry, this right here. Okay, so if you don't have that and you just go straight to the answer of what ux is, you don't show your trigonometry working out, you can lose a mark. And then you get a second mark for calculating that the horizontal component of the initial velocity is 6.06 meters per second to the right. All right, so really you need to recognize that trigonometric relationship between the initial velocity and horizontal component. Okay, just really I guess revise your vectors and how trigonometry relates to this physics component concept, right? And we know that since the horizontal acceleration is equal to 0 meters per second, and ux is going to be constant. Okay, so that's an interesting mark, but they actually gave a mark for recognizing that horizontal acceleration is 0. Okay, so that's another reason why I wanted to emphasize this formula instead, because we need to write down a fact about a, lowercase a, that a in terms of the x component is going to be assumed to be constant. Assumed to be 0, that there's no acceleration. All right, there's no wind blowing that makes the object go faster or slower in the x direction. Okay, the only acceleration we're working with in year 12 physics is the acceleration due to gravity in the vertical displacement. Okay, so that will basically assume that ux is going to be constant. Okay, so I thought that was an interesting mark they gave, but it's really just about showing, full working out. If you have your formula such as s equals ut plus half at squared, you can notice that when a is equal to 0, because if we're talking about the x components now, then that means we just get rid of this part of the equation. We're left with sx equals uxt. So I basically just derived that year 12 formula that we got. That's how we get that formula, and why it's different to the sy, because we don't have an acceleration. We don't have a meters per second squared. Alright, so therefore sx equals uxt, okay, as I mentioned, and that's going to be equal to 6.06 times my time, which is given, so another fact, 0.71 seconds. So you can go between the 5 f's, but make sure you don't forget them or make silly mistakes. and then I get my answer. Is equal to 4.3026 meters, okay? Or I could just say that it was 4.3, okay, just to round it a bit nicer there. Okay, so approximately 4.3 meters is my horizontal displacement, or my SX, okay? And that gives me my full marks for that question. So thank you so much for watching. If you have any suggestions, let me know in the comments, or message me on my Instagram, Louis Galman. And all the best for studies.